My name is Liesbeth Arnouts. I am currently finishing my PhD about deployable structures at both the Vrije Universiteit Brussel and the Universiteit Libre de Brussel. I am incredibly honored to have been awarded the Hangai Prize, and I would like to thank the IASS for the recognition of my work in the field of spatial structures. Moreover, I would hereby like to thank my supervisors, without whom this achievement would have been impossible. So today I'm going to talk about the structural optimization of bistable scissor structures, and more specifically about a coupled sizing, shape, and topology optimization methodology. What are bistable scissor structures? Scissor structures consist of scissor-like elements, which are assemblies of two beams connected by a revolute joint. In the folded configuration, scissor structures are compact, and they can be rapidly deployed while offering a huge volume expansion. Because of a design that is more straightforward, stress-free scissor structures have been used preferentially in the past, but these mechanisms have the disadvantage that they need external manipulation to bear loads in the service state. Another approach consists of introducing geometric incompatibilities during transformation, leading to the bending of some specific elements. These structures are called bistable, and they exhibit a snap-through phenomenon to instantaneously achieve a structural stability in their deployed state. The main characteristic of deployable structures is that they are both mechanisms and structural systems, which means that they transform and that they can bear loads in their service state. The main challenge is to obtain structures that are lightweight, easy to transform, and self-supporting in the deployed state. These requirements are often contradicting, and the challenge is thus to find an acceptable compromise. To find this compromise, I developed an optimization methodology for bistable scissor structures. The structure that I consider in this presentation consists of square scissor modules. Two types of modules are used, which are non-bistable deployable modules, or NBDMs, and bistable deployable modules, or BDMs. The outer scissor-like elements always remain straight during transformation, while the inner scissor-like elements bend during transformation. This means that when the diagonal elements are removed from a bistable module, the module becomes a pure mechanism. The structure that is used to demonstrate the methodology is a curved wall of 5 times 5 modules. The length and height of the wall are around 2 meters in the service state. The wall could be used for privacy, branding, screen projection, exhibitions, etc. Abacus is used for the detailed analysis of the nonlinear transformation phase, as well as for the linear analysis of the deployed configuration. Beam elements discretize the structural members, and hinges are used to simulate the connections. A spacing between the beams is taken into account because in reality, the two beams in the scissor-like element do not lie in the same plane. The hub dimensions have been taken into account by using a stiff grid of small beam elements. The bottom points of the structure are fixed in the vertical direction since the structure is standing on the ground. During transformation, the upper points are subjected to a vertical displacement. In the service state, a banner, which is a plastic layer, on 2 sides of the structure is moduled by vertical forces on the upper points corresponding to the weight of the banner. On the load displacement curve, point A is the initial deployed configuration. When folding the structure, some of the beams bend, requiring an increasing force. The peak load is reached at point B, followed by a snap-through. Point D can be considered as the final folded configuration. There are some important criteria to consider. The peak load should be limited to ensure an easy transformation. The snap-through magnitude should be limited to ensure safety, and the stresses inside the beams should be limited to ensure an elastic material behavior. The challenge of obtaining a flexible structure during transformation, which provides stiffness in the deployed configuration, can be translated as a multi-objective optimization problem, in which the objectives are to minimize the peak load and the deflection in the service state. The considered constraints are the stress, which should be limited to ensure elastic material behavior, the deflection, which is chosen to be lower than the span of the structure divided by 100, and the local buckling. For the beams, circular hollow cross-sections of 1 mm thickness are chosen. In total, 3 continuous design variables are defined: the diameter of the outer azimuth, the diameter of the inner azimuth, and the position of the center points. The position of the center point is a variable because its value influences the intensity of the snap-through effect. The lower and upper bound for the outer diameter of the cross-sections are chosen corresponding to available profiles on the market. The limits for the center point are chosen in a way that this point cannot be located outside of the volume envelope of the module. The forces and stresses are sampled at each increment of the finite element simulations using the NSGA2 algorithm. The approach is given here on the right. An initial population is chosen randomly. An offspring population is created by applying crossover and mutation operators by picking parents from the first population. From the parent and offspring generation, the best members are chosen, and this procedure is then repeated until convergence is reached. Now, a new step is proposed, which is topology optimization. In this step, the number of bistable modules is optimized by finding the location of bistable modules, yielding mixed structures of bistable and non-bistable modules. To do this, inner scissor-like elements are removed selectively. Switching bistable modules to non-bistable modules reduces the snap-through effect, as well as the mass and the complexity, but also reduces the stiffness of the structure in the service state. To choose which modules to replace by non-bistable ones, a discrete topology optimization approach is proposed. Binary variables are used to assign a value 0 corresponding to missing inner azimuth or 1 corresponding to present inner azimuth to each module in the structure. There are 25 modules, however. Since there is some symmetry, the design variables can be reduced from 25 to 15. Similar to the shape and sizing optimization method, the NSGA2 algorithm is used to minimize the peak load and the deflection. The constraints are chosen to be taken into account only in the shape and sizing optimization step. When we use only the shape and sizing optimization approach, we obtain this Pareto front. In reality, there is a limit on the peak load, taken here as 0.5 kN, since an easy transformation is desired. The objective of combining this step with topology optimization is to further reduce the transformation load next to reducing the complexity, weight, and cost of the structure. When we only use a topology optimization, we obtain the Pareto front on the right figure. For the structure consisting of only bistable modules, the result is given by the red circle. 37 optimal configurations were obtained, given by the blue circles. However, some solutions were filtered out, denoted by the unfilled circles, because other solutions with a lower mass and the same transformation load and deflection existed, resulting in 29 non-dominated configurations, which you see in the left figure. The less bistable modules, the lower the transformation load and the higher the deflection. Note that it is not guaranteed that these optimized solutions will lead to feasible solutions, since no constraints are taken into account. The optimization approaches were combined, and the different sequencing of the approaches was investigated. On the left, you see the results of doing the shape and sizing optimization first for 4 randomly chosen results from the topology optimization. When the results are recalculated for a different topology, a new Pareto front is obtained. The red points are solutions that do not satisfy the constraints after changing the topology. This sequence requires thus a final verification step in which these solutions are eliminated. While the decrease in peak load is modest, the complexity of the structure and its weight are reduced significantly. On the right, there are some solutions of doing the topology optimization first. Since the shape and sizing optimization is performed on a chosen optimized topology, all optimum solutions satisfy the constraints. The main disadvantage is that for each different topology, a costly shape and sizing optimization is required. For cases in which the topology is similar to the structure consisting of only bistable modules, the figure on the top, the difference between the sequences is rather limited, while for other cases, the difference increases. Performing the topology optimization first is advisable, since it leads to more optimized solutions. This is the resulting proposed computational design methodology for bistable deployable structure. In this methodology, the geometric design is combined with the structural analysis and an optimization algorithm. First, the topology optimization is performed, which results in a final grid, which is used for the shape and sizing optimization. To conclude, a design methodology combining topology optimization and shape and sizing optimization was elaborated for bistable scissor structures. A topology optimization step was incorporated to optimize the topology at low computational cost. The shape and sizing optimization is computationally expensive, and it is recommended to use it as a final step for fine-tuning the results. Coupling the two optimization approaches results in solutions with a lower transformation load, lower weight, lower cost, and decreased complexity. The resulting design methodology could be an important step towards increasing the application potential of bistable scissor structures. So that was it. Thank you for your attention.